and welcome to section 2.2 of chapter 2, which is has to do with polynomial and rational functions. So 2.2 deals with polynomial functions of higher degree. So what are our goals? Our goals are to use transformations to sketch graphs, learn the leading coefficient test to determine how the graphs look like at their ends, the end behavior, how to find and use the zeros of polynomial functions to help draw the graph, and then finally use the intermediate value theorem to help also locate real zeros. Okay, so let's get into it. Graphs of polynomial functions. So in this section, we're talking about different graphs of polynomial functions. So, and we're talking about their characteristics. So one characteristic is that the graph of a polynomial function, we say it's continuous. Polynomial functions have continuous graphs. What does that mean, continuous? That means that there's no breaks, no holes, no gaps. Okay, so it just keeps going through like this. This is a piecewise function here that is not continuous, right? So this is not a polynomial, it's a piecewise defined function. Like maybe this piece is a polynomial and this piece is, but together it's like, not continuous. So another one is that the graph of a polynomial function has only smooth turns. So notice that this is like a smooth edge, a rounded rounded corner, a rounded maximum, minimum, maximum, minimum. So we cannot have a sharp turn. So you cannot have a so for example, absolute value of x, notice how it has this pointy, it looks like a V. We can't have this. This is not a polynomial function. Well, in fact, absolute value of x is defined as, x and then negative x this way. So yeah, it's kind of like a piecewise, right? So the graphs of polynomial functions that are greater than 2 are a little bit more challenging to look at than the graphs of 0, 1, or 2. So linear, a constant, second degree quadratics, right? So if we go through this and we use what we know about intercepts, plotting points, and symmetry, we should be pretty good to able to just sketch things by hand. Okay, so polynomial functions that have the simplest graphs are monomials of this form: f of x is equal to x to the n, where n is an integer greater than 0. Okay, so let's look at a couple of examples. From these images, you can see that when n is even, the graph is similar to the graph of f of x is equal to x squared, the squaring function. So let's say here, x to the fourth looks like it. And then when n is odd, it looks kind of like x cubed. So see here, this is an even. It touches the axis at the x-intercept. Here it crosses the axis. It kind of does this wavy thing. All right, so the larger n gets, the flatter it is near the origin. So you see here, it's kind of like looks flat, and then here it's also flatter. This is x to the 5th power. This is x cubed. Okay, so how would we sketch the graph of each function? Okay, so x to the 5th is an odd function, and so it would probably go like this and come up here. We saw that before, but because it's negative, you have what happens when you have negative of a function? It reflects across the x-axis. So now you have a twisty, turny function that goes down this way. Okay. And then B, the graph of h of x is equal to x plus 1 to the 4th. It's going to be this big one, right, with a rounded edge here, kind of squished more than a regular parabola, because this is a quartic function, 4th degree. And then because it has a plus 1, that means it goes to the left one. It's a left shift by 1 unit of this graph. Okay, so sorry, the leading coefficient test. All right, so what is the leading coefficient test? So in this example, we need to think about in graphs, like both graphs usually go up and down. So graphs go, what happens to their end behavior? So the leading coefficient test helps us to understand what happens at the end, whether it goes up or down, or whether it stretches out to, really there's only two choices. It could go up or down, unless it has like an asymptote where it approaches the x-axis. But when we're talking about polynomials, we can tell whether how the end behavior is depending on what degree it is and if its leading coefficient is positive or negative. So let me get into what that is. So if you have here going from left to right, or if you're looking at x as it goes to negative infinity or positive infinity, the graph of a polynomial behaves like this. Okay, so if it's odd, if the degree of the polynomial is odd, if it's a positive leading coefficient, meaning like the number in front is positive, as x goes to negative infinity, f of x will also go to negative infinity. And as x goes to positive infinity, f of x also goes to positive infinity. We don't exactly know what goes in the middle, but we do know how it ends up on the endpoints, okay? Or not points, but the ends of the function of the graph. Okay, and if it's negative, it's basically this, but you flip it, right? So as x goes to negative infinity, the y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. So it's kind of like goes this way, and if it's positive, it goes up this way. Okay, now if it's an even number, we know that they either both go up or they both go down. But if it's positive, if the leading coefficient is positive, then both ends go up. And if it's negative, both ends go down. Okay, and then so let's go ahead and apply the test to some functions. So you can push pause, and then you can tell me what you think the right and the left-hand behavior of these next graphs will be. Okay, so go ahead and push pause and either write it down or at least think about it, and then we'll go through the answer right now. Okay, so example 2a, so we have here, because the degree is odd, okay, so it's negative x cubed, yeah? And the leading coefficient is negative, so as x goes to negative infinity, y goes up, and then as x goes to positive infinity, it's going to go down. So it's like this way, okay? It's kind of like it decreases, and then something happens in the middle, but ultimately it goes down this way. The next one, it was x to the power 4, so we know that it's an even, so they either both go up, both go down, but if it's positive, then they both go up. And then the C, it's odd, so we know it's going to go one or the other, like one way is going to go one way and the other one's going to go this way. But because it's positive, as x goes to negative infinity, y goes to negative infinity, so it goes downward. And then as x goes to positive infinity, y goes up. And then, so notice that the leading coefficient test, it only tells you if the graph rises or falls to the right or left. So it just tells you the end behavior, okay? It doesn't really tell us like what's going to happen in the middle or what kind of funny bumps it does. It just tells you what happens at the ends of the graph, like whether it shoots up to positive infinity or shoots down to negative infinity, and so on, and whether they're both the same or they're both different. Okay, so really not too bad. Okay, but how can we tell it, what's going on in the middle? And part of that is finding the zeros, yeah? So if we find the zeros, that kind of gives us a closer picture of what's going on in the middle of the function. Now that we know the leading coefficient test will tell us what happens at the ends, right? The end behavior, in other words, this will tell us the middle. So, or not all of the middle, but some of it. So let's see here. So if we have a polynomial function of nth degree, we can say the following things. The function has at most n real zeros, and the graph of f has at most n minus 1 turning points. at most. And remember the word at most. It means that it's not going to have any more than that, but it could have less. There is a possibility that there's less, okay? So turning points are also known as, we've seen it before, as minimum and maximum, but they're relative minimum, relative maximum. They're points where the graph changes from increasing to decreasing and vice versa. So this is really important. So, so it's really cool. So it's really cool because graphing and algebra help us to really create a whole picture. So I want to tell you a couple of things because these statements that we're going to go over, they're all equivalent. So if you hear me saying something, or if you read something in the book, any of these four things, they're all talking about the same thing. So we need to make sure we understand. When you say x equals a is a zero of the function f, that means that it's a solution when f of x is equal to 0. Literally, it's called a 0 because if you plug that into the function, you get 0. Not too bad. That also means that x minus a is a factor of f of x. That's really important, and we're going to talk about that more in depth later, but just, plug that away into your brain. And then 4 is that a comma 0, that point, is an x-intercept. Well, of course it is, right? Because any point that crosses the x-intercept has the value of f at that point is 0. So there you go. Okay, see how it's connected? It's all connected. Okay, so example 3. Let's find the real zeros of f of x is equal to negative 2x to the 4th plus 2x squared. Then let's determine the maximum number of turning points of the graph of the function. Okay, so if we want to find the real zeros, let's set f of x equal to 0 and solve for x. So, okay, so we set that equal to 0. What can we do? We can factor, yeah? So we factor the greatest common factor. So let's say we take out a negative 2x squared. That gives us x squared minus 1 is equal to 0. But of course, we know by now x squared minus 1 is difference of squares. And if we factor that, we get negative 2x squared, x minus 1, x plus 1. So you have the zeros 0, 1, and negative 1. So also, because the function is a 4th degree polynomial, the graph of f can have at most 4 minus 1, which is 3 turning points. Okay, so what does that look like graphically? It looks like, okay, so this graph has 3 turning points. So it goes from negative to positive, it increases here. It increases and it changes direction here to decreasing, then it changes direction again to increasing, and then changes direction again to decreasing. In other words, it has, this is a maximum relative to everything else, right? So if I just look within this little circle, I'd see that's the maximum value. This is a relative minimum, because if I was to draw a little box or a little circle just around here, I would see that this is the lowest possible value, and this is a relative maximum, because same reasoning, right? So if you just ignore everything else except like this little circle around the top, that would be the maximum point. Okay. So what else? So we know that because we notice that this factor, something weird is happening at x squared, yeah? At 0, we call this a repeated 0 because there's 2 of them, right? In other words, another way that they've said it before is they just will say a 0 with a certain multiplicity, meaning it happens that many times, multiple times, yeah? So let's say you have a factor of the form x minus a, where a is the 0, to some power k that's greater than 1. We call this, the book calls this a repeated 0, x equals a of multiplicity k. I'll probably use 0 with multiplicity because that's the way that I learned it, but just so you understand what the book is saying, it says a repeated 0, which makes sense because it repeats. But the multiplicity will tell you how many times how many times the 0 happens. So like here, it's a multiplicity 2. It's basically the degree. Okay, and in this case, of course, a would be 0, right? Because there's nothing there, and see how it touches here at 0. Now, why do we care about repeated zeros of a certain multiplicity? Well, if k is odd, it tells us about the graph, of course, like always. So if it's odd, it's just going to go straight through like this or like this, right? But if k is even, that's the interesting part. So what happens is the graph touches the x-axis but then bounces back up or back down depending on where it comes from. So it kind of like, it's like a vertex of a little mini, hill, like a mini valley or a mini hill, depending on what the rest of the graph is doing. Okay, so it just kind of touches the axis, but it does not cross. And that only happens when it's even. Okay, so to graph, we need to use the fact that polynomial functions can only change signs at its zeros, if it does change signs, right? Unless you have, of course, a factor of even multiplicity. So let's say here, between two zeros, right, the function, so you have these two zeros, the function is either entirely positive or entirely negative, which makes sense, right? Because these two zeros are next to each other. There's no other place where they're crossing and changing signs. They're either, it's all positive or all negative, right? So, yeah, so in this case, it's all positive, and then between these two zeros, it's still all positive. If there was another zero over here, it would be entirely negative. So between these two zeros, it's entirely positive. Between these two zeros, it's entirely positive. And also, at its zero, it can change signs or it can't, or it doesn't. So at the zero itself, it goes from negative to positive here. And then from here, this zero, it goes from positive to negative. The only exception would be, let's say, for example, something here where you have a factor of an even power multiplicity. So this here has a factor of multiplicity too, so it doesn't change signs at the zero, and instead it just goes from positive back to positive. So another thing you can do, so if you wanted to put the real zeros in order, you see how it divides the number line into intervals where the function has no sign changes in between the zeros. So we could call these things test intervals. So if I was to draw a straight line and I would put -1, 0, and 1, I could plug in points to see where the graph is so that I know, and if I just plug in 1 point, because it's in between two zeros, I know it's going to be that value the entire time. So let's say, for instance, between -1 and 0, if I plugged in negative 0.5 and it's positive, it's going to be positive for all this interval. So if I did that here, it's positive for all this interval, and if I did one here, it's going to be negative, and so on. Which leads me to the intermediate value theorem. It's something that is kind of instinctual, but we need to state it. So what is the intermediate value theorem? Okay, so it basically says take 2 points on the function that are different, okay, 2 distinct points on the graph. Then let's say if I had any number between the y values of this graph, right? So here are my 2 points, f of a and f of b. X coordinate a, y coordinate f of a, x coordinate b, y coordinate f of b. So I have these 2 points, and let's say I have some value d here. And d is between f of a and f of b, yeah? So for every value that's in between this interval, there exists an x value between the x's that points to that first value d, okay? So there exists a value c such that f of c is equal to d. So what does that mean? That's basically saying, hey, because it's continuous, there's no holes and stuff, there's no discontinuities. If for any, let's say, as f of a increases and becomes f of b on the graph, there is, and for every point that's in that interval, there exists another point in the x of x value between a and b that points to it. So why do we care about that? That helps us to locate real zeros of a polynomial, meaning that if you have a negative f of something and a positive, so a negative y value or a negative function value and a positive, we know that there has to be a zero in between. We know that there exists a zero because numbers change from negative to positive at 0. Okay, so let's look at this example. So let's say here this function x cubed plus x squared plus 1, it's negative at the value x equals 2, negative 2, and it's positive at x equals negative 1, right? The function value at negative 1 is positive 1, and the function value at negative 2 is negative 3, okay? So in other words, the y is negative 3 here, and the y is positive 1 here. So that means there has to exist a 0. There has to exist a point where the function changes sign, yeah? So that's where we have to, we know, because of that, we know that there exists a 0 between negative 2 and negative 1, okay? But we don't know what it is exactly, but. Okay, so let's do an example. If we wanted to do, use this theorem to approximate a 0, we could go ahead. We'd start by plugging in some function values. So we'd create a table, yeah? And we'd plug in like negative 2, negative 1, 0, 1, and we'd see our answers. We'd get negative 11 for negative 2, negative 1 for negative 1, 0 is 1, and then 1 is 1. So here we start, we're getting interested, right? So algebraically, we're like, oh my gosh, look, the sign of f changes from negative 1 to 0. It becomes positive. So we know now by intermediate value theorem, we know definitively that there's a 0 there. So what we can do is we can just keep dividing the interval into tenths and evaluate the function at each point. So if we kept going and going, we'd find that between negative 0.8 and negative 0.7 is the 0. So we'd have negative 0.152 here and 0.167 here, okay? So there has to be a 0 in there. And if we wanted to keep going, we would have to just apply values between that interval and keep doing intermediate value theorem. So if we kept doing this, we would get a 0 approximation to whatever accuracy we want. We can keep going and get smaller and smaller and smaller and eventually get to it. However, it's nice that we have technology, so I'm going to show you how to find zeros using your calculator anyway. But I just want you to know the theory, okay? So, but when you're applying it, it's easy. You can do a calculator, so I'll show you. Okay, so we go to y equals, and we enter our function. There it is, x cubed minus x squared plus 1. All right, so we do that, and then once we've entered it, we go to, let's look at the graph. The graph is right there. I can't see it that well, so let me zoom in. I hit zoom in, enter, and then I go kind of hovering over the 0, and I click enter. So I move my cursor to the 0, enter. See how it like zooms in like that? That looks good. Okay, fine. Now I'm going to calculate, go to 0, hit enter. Okay, and I'm going to give the graph I'm going to give the calculator a guess. So I think it's to the left of this, and then I'm going to go to the right of the 0, hit enter, and then I'm going to go down and kind of scroll on top of it and hit enter, and it's going to give me my 0 back. So my 0 is actually negative 0.754, 8, So that's a really close, that's very close. The intermediate value theorem took us where we needed to go, but the calculator will just speed up the process. Okay, so that's it. For me, your super fun homework is section 2.2, 1 through 55 odd, 67 to 73 odd. Be on the lookout. I'm going to post some worked out examples on a PDF for chapter 2 shortly. So that way when we're doing homework, you can refer to those and then you can kind of go back and practice some more. Alrighty, so I will see you guys on the next video.